In today's lesson, we shall be looking at classification of second order PDEs. Classification of second order PDEs. This is what we'll be looking at in today's lesson. If today is your first time seeing my video and you really like it, you can hit on the subscribe button for me. You know, second order PDEs are PDEs in which the highest partial derivative present in that equation is of order 2. So all these examples are second order PDEs. This is a second order PD. This is also a second order PD, and then this is also a second order PD, because the highest derivative present in each of these equations are of order 2. So this is order 2, order 2, order 2. Each one of them, the highest partial derivative within them are of order 2. So all these are examples of second order partial differential equation. Now, second order partial differential equation can be classified under parabolic, hyperbolic, and then elliptic, depending on the value of the discriminant. Depending on the value of what? The discriminant. So we are talking about the discriminant. The discriminant can be obtained from the characteristics equation of a second order non-homogeneous differential equation, which is given as dy over dx. It is given as what? Dy over dx is equal to b. We are plus or minus the square root of b squared minus 4ac all over what? 2a. So this is the characteristics equation of a second order differential equation. The characteristics equation. Now the expression under the radical sign. So looking at this, the expression under the radical sign, which is b squared minus 4ac, is what we call the discriminant. Is what we call what? The discriminant, and it is written as this, and then we have b squared minus 4ac. So it is this discriminant that is going to help us classify PDEs under parabolic, hyperbolic, and then elliptic. What does this discriminant say? It says that if it is 0, if the discriminant is 0, if is equal to 0, then we say that that equation, that PDE, is a parabolic equation. Is what? A parabolic. Also, if the discriminant is greater than 0, then we say that the equation or the PDE given is an hyperbolic. And then lastly, if the discriminant is less than 0, then we can say that that PDE given is what? An elliptic. So these are the three cases that we are having. If the discriminant given is equal to 0, then we can say that that equation is what? A parabolic differential equation. And then if the discriminant is greater than 0, or it is a positive number, after calculating for your discriminant and you are getting a positive number, then you can say that that equation is what? An hyperbolic equation. And then when you do your calculation for the discriminant and you realize that you are having a negative number, then we can say that that equation is an elliptic equation. Very, very easy and then simple. Someone may ask, how do we get our B, our A, and then our C to do our calculation? The A, B, and C can be obtained from the principal parts of the equation that will be given. So with the principal part, we are looking at the highest partial derivative within that equation that will be given. Since we are looking at the second order, the highest partial derivative is going to be what? Order 2. So we are going to look at the xx, the xy, and then the yy. So the principal parts are the highest partial derivative in that given equation. So we have uxx, uxy, and then uyy. We call them the principal parts. The coefficient of uxx is what we call the a. The a represents the coefficient of what? Uxx. The b represents the coefficient of uxy, and then the c represents the coefficient of what? Uyy. So let's take that particular example and then see something. We have 4uxx plus, let's say, minus 3uxy plus, let's say, 6uyy. Let's make it is equal to, let's say, 0. So we have the principal parts. So these are the principal parts. The coefficient of uxx is called the a. The coefficient of uxy is what? The b. And then the coefficient of what? Uyy is what? Is c. Please kindly take notes. If you have a second order differential equation of this form, let's say 6u xx, and then we have plus, let's say, 10u yy is equal, let's say what? Sine x. And then we have to find our a, our b, and then our c. So these are the principal part, the highest partial derivative in that equation. So the coefficient of uxx is what? A. So we have our a is 6. Our b is the coefficient of what? Uxy. We don't have uxy here, so it is 0. And then our c is the coefficient of uyy, and that is what? 10. Very, very easy, and then simple. Can you take note of that? So now that we know all of this, we want to classify the following PDEs under parabolic, hyperbolic, and then elliptic. So we have the first part A, B, and then C, and then we have another second part. Now let me explain this before we start. If you have a differential equation in which the coefficients of the principal part are all constant real numbers, then surely we are going to have any one of these. That equation is going to be either parabolic, hyperbolic, or elliptic. If all the coefficients of the principal part are all constant real numbers, then we are going to have one of these. We are going to have one of these. That is when the coefficient of all the principal parts are constant real numbers. Now, what if any of the principal parts are having a coefficient of variable, or we have a variable coefficient of any of the principal parts? If that happens, then we are going to have 2 or 3 of these cases. It means that that equation is going to be either parabolic, hyperbolic, elliptic, or all of the 3 cases, or 2 of these 3 cases. If the coefficients are what? Variable, you can have 2 of these cases or 3 of these cases. So looking at this example, I have splitted them into 2, the one with constant coefficients and the one with what? Variable coefficients. We are going to classify them under these 3 instances, or these 3 cases: the parabolic, hyperbolic, and then elliptic. So let's start with the constant coefficients. The constant coefficients. So let's start with the first one. We want to determine if this equation is parabolic, hyperbolic, or elliptic. So in doing that, we are going to make use of what? The discriminant, which is this one, to determine if the value that we are going to get is going to be 0, is going to be a positive number, or a negative number. Since we are having constant coefficient of the principal part, definitely we are going to have any of these, one of these. So first we have to find our A. Our A is the coefficient of what? Uxx, and that is 1. Our B is the coefficient of uxy, that is what? Minus 3. And then C is the coefficient of what? Uyy, that is what? Minus 10. So once we have this, we plug it into the discriminant. So we have b squared, this is b, so minus 3 all squared minus 4. Our a is 1, so we have times 1. Then we have our c is what? Minus 10. So this is giving us what? 9 minus what? This is going to give us 40, right? So when we add them, we are getting 49. So you can see that the discriminant is a positive number, and this positive number is greater than 0. So what type of equation is this? What type of equation is this? So we said that if the discriminant is greater than 0, if the discriminant is greater than 0, a positive number, then that equation is what? An hyperbolic. So this equation is an hyperbolic equation. So we have hyperbolic. So it means that this equation is an hyperbolic equation. Very, very easy and then simple. Let's look at the second one, which is B. So with the same approach, we are going to identify our A. So this is B, this is A. Our A is the coefficient of what? UXX, that is 4. Our B is the coefficient of UXY, that is also 4. And then C is the coefficient of what? UYY, that is what? 1. So we have 4, 4, and then 1. Then we write our discriminant. So we have our B squared. B is 4, so we have 4 squared minus 4. Our A is also 4. And then our C is also 1. So this is going to give us what? 16 minus what? 16. And that is equal to what? 0. And we say that whenever the discriminant is equal to 0, what happens to the equation? The equation becomes what? A parabolic equation, because the discriminant is equal to 0. So that equation, the second equation, is what? A parabolic equation. And then simple, let's look at the last one, which is C. You can pause the video and then you try your hand on it. So with C, our A is the coefficient of UXX, that is 3. Our B is the coefficient of UXY, that is 5. And then our C is the coefficient of what? UYY, that is what? 3. So we have our discriminant, B squared minus 4AC is equal to what? We don't know. So we have B squared, we have 5 squared minus 4. Our A is 3. Our C, is also 3. So this is going to give us what? This is giving us 25 minus what? 99436. And when you do your subtraction, you are getting negative 11. Good. And we can see that negative 11 is a negative number. And we are saying that if the discriminant is less than 0 or a negative number, that equation becomes an elliptic. So example C or question C is an elliptic equation. So we have elliptic equation. Very, very easy. So you realize that when the principal parts are having constant coefficients, it is very, very easy to identify the type of equation it is. Now let's look at the one that involves variable coefficients. So we are done with the constant, we are moving on to the variable. So we want to determine the region of all points at which the PDE is hyperbolic, parabolic, and then elliptic. So it means that since we are having variable coefficients like this, we can have the equation to be a parabolic, hyperbolic at the same time. It can be also parabolic, hyperbolic, and then elliptic at the same time. It can be all the 3 cases or the 2 cases. So we are going to start with So let's start with the last one, which is the remove to this, the remove to that. So from the last one, C, so we have C, our A is the coefficient of UXS, and that is what? X. our b is the coefficient of uxy. We don't have uxy here, so that's going to be 0. And then our c is the coefficient of uyy, and that is what? 1. So once we have it, we plug it into the discriminant. So we have our b is 0, so we have 0 minus 4. Our a is what? X, and then our c is what? 1. So we are going to have 4 minus what? 4x. So you can say that the discriminant is equal to negative 4x. So this is what we are getting. We have the discriminant to be what? Negative 4x. So looking at this, you can see that we are not getting a constant real number where we can say that, oh, because it is 0, it is parabolic, because it is negative, it is elliptic, because it is greater than 0, it is what? Hyperbolic. But what we are seeing here is what? An expression. So we have the discriminant to be an expression. So because it is an expression, we have to do some small analysis before we can determine that, oh, the equation is a parabolic, an hyperbolic, or elliptic. So we are going to do small analysis, because if you remember, I said that if the coefficient of the principal part, any of the coefficients of the principal part are having variable coefficient, then we can have 2 cases, or we can have 3 cases all happening at the same time, and that is what we are having here. So this is what we are going to do. We are going to take all the cases one after the other, and we are starting with what? Parabolic. So we said that the equation is parabolic if the discriminant, so the discriminant b squared minus 4ac is equal to 0. So if the discriminant is equal to 0, then we can say that the equation is what? Parabolic. So our discriminant here is minus 4x. So we have minus 4x, and this is equal to 0. We want to check to see if it is really parabolic. The equation is parabolic. So from here, we can divide both sides by negative 4, right? So that this will cancel this. So we have our x is equal to 0. So this is what we are having. So it means that the equation is parabolic if x is equal to 0. So we have our first one. The equation is parabolic if x is equal to 0. Now that we are done with the parabolic, we move on to the hyperbolic. So we say that the equation is hyperbolic if the discriminant, so the discriminant is what? Which is b squared minus 4ac is greater than 0. So from here, our discriminant is what? Minus 4x. So we have minus 4x is greater than what? 0. So let's divide both sides by negative 4, right? So this will cancel this. So we have our, since we are dividing by a negative, the sign will change from greater than to what? Less than 0. So we say that the equation is hyperbolic if x is less than 0. Very, very easy. And then move on to the last part, which is what? Elliptic. Elliptic. So we say that the PDE is an elliptic if the discriminant b squared minus 4ac is less than 0. Here our discriminant is minus 4, so we have minus 4x is less than 0. So let's divide both sides by minus 4. So this and that will go. So we have our x. The sign will change from less than to what? Greater than 0. So we can say that the equation is elliptic if what? X is greater than 0. So it means that with this particular PDE, it is parabolic, it is hyperbolic, and then elliptic. That is why earlier in the beginning I said that if the coefficient of any of the principal parts are having or is having a variable coefficient, then the equation can be parabolic, hyperbolic, or elliptic at the same time. And we have seen that instance here. We are having parabolic, hyperbolic, and then elliptic. So this equation is what? Hyper, para, and then elliptic at the same time. Now, looking at the question, it says that we are to determine the region of all points at which the PDE is hyperbolic, parabolic, and then elliptic. We are to determine the region of all points. So with that one, we are going to sketch, right, to help us determine all these points. So we are going to sketch our x and y plane. We sketch what our x and then y plane to determine which points on this x and y plane that makes the PDE parabolic, hyperbolic, or elliptic. So we have our Cartesian plane or x and y plane. This is the origin. So let's start with the parabolic. So we are saying that x is equal to 0. So we want to determine all points. We want to see which point on this Cartesian plane will make the PDE what? Parabolic. So we are talking about what points. So we are going to use points from the Cartesian plane to verify this equation. So we have x is equal to 0. So which point on this Cartesian plane will make the x to be equal to 0? You can see that when we pick a point here, we are going to have 0, and then let's say 1. When we pick a point here, we have 0, and then 2. We pick a point here, we have 0, and then let's say 4, and so on. So any point, when we pick a point here as well, we are getting 0, -1. We pick a point here, we are having, let's say 0, and then -2. We pick a point here, we have 0, and then let's say -10. So any point on this particular line, makes the PDE what? A parabolic. So any point on this line. So we have our s is equal to 0. So it means that any point on this particular line makes the PDE what? Hyperbolic, because we are determining all points which makes the PDE what? Parabolic. So we are done with the first one. Then we'll move on to hyperbolic. So with the hyperbolic, we are using its inequalities. So we have x is less than 0. So we have x is less than 0. So it means that we are going to use point to determine whether this inequality is true or not. So let's pick any point on the x-axis. So let's pick a point here. The point where we are going to pick here, we have 0, so definitely here is going to be 1, 2, 3, 4. So let's say 2. The point here 2. Is 2 less than 0? Nah, this is not true, because 2 should be greater than 0, but we're having 2 is less than 0, so this is not true. Let's come to the left hand side. Let's pick a point here. We have negative, let's say 3. So we have x is less than 0. Let's plug in to see if this inequality will be true. So you have -3. Is it less than 0? Yes, you can see that it is true. Now let's take another number. Let's say -10. Is -10 less than 0? You can see that it satisfies the hyperbolic inequality, which says that x is less than 0. So you can see that any point that we pick on the left hand side, satisfies the hyperbolic inequality. So it means that any point here makes the PDE an hyperbolic equation. So we are done with this part. Let's move on to the elliptic. So the elliptic inequality says that x is greater than 0. So we have x is greater than 0. So we are going to test to see if this is actually true with points. So if you have to pick any point in this region, let's say the point is here, let's pick a point here. So the point here, let's say this is 2, and then let's say -5. Our x-axis is our x coordinate is what? 2. So we have 2 is greater than 0. Is it true? Yes, it is true that 2 is greater than 0. Now let's pick a point here. Let's say 7, and then let's say 7 and 10. Our x coordinate is what? 7. Let's plug in. 7 is greater than 0. Is it true? So it is true that 7 is greater than 0. So you can therefore say that any point that we pick here makes the PD an elliptic because it satisfies the equation, the inequality x is greater than 0. Very, very easy. So always we have to test with points from the graph to see if it satisfies that particular inequality or equation. So this means that this area is x is greater than 0. That is what? Elliptic. So you can say that this area, this region is what? Elliptic. Elliptic. This area is also elliptic. This area is what? Hyperbolic. And then on this line, the equation is what? Parabolic. Very, very easy and then simple. I guess you are following. Let's look at B. Let's look at B. So with B, our A is the coefficient of uxx, that is y. Our B is the coefficient of what? Uxy, that is -4. And then our C is the coefficient of what? Uyy, that is 4x. Then after that, we write our discriminant. We have b squared minus what? 4ac. We are going to plug in this. B squared is what? -4. We have all squared minus 4. Our A is y. Our C is what? 4x. So this is giving us what? 16. Then we have minus 16 xy. So this one also, you can see that our discriminant is an expression. It's what? It's an expression. So we can't just stick that the equation is parabolic, elliptic, or hyperbolic. We have to analyze the expression before we can come out with our conclusion that the PD is what? Parabolic, elliptic, or what? Hyperbolic. So we are going to analyze it like the earlier example that we did. So we are starting with what? The parabolic. So we say that the equation is parabolic if the discriminant b squared minus 4ac is what? Equal to 0. So from here, our discriminant is what? 16 minus 16 xy and is equal to 0. So we are going to solve the discriminant here. So from here, we can decide to send this to the right hand side so that we have 16 is equal to 16 xy, right? And we can see that 16 will cancel 16. 16 will cancel 16. We are left with what? 1. 1 is equal to what? Xy. Or we can say that our xy is equal to 1. So you can say that the equation is parabolic if xy is equal to 1. So we have our first one. Then we move on to the hyperbolic. So the hyperbolic, we know that the discriminant. So we have the discriminant 16 minus 16 xy is what? Is greater than 0. So when we do some small algebra here, we are going to have our 16 is greater than, let's send this one here, 16 xy. When we divide both sides by 16, we have our 1 is greater than what? Xy, which we can write it as xy. Our xy is less than what? 1. So from here, we are saying that the equation is hyperbolic if xy is less than 1. Then move on to the last instance, which is what? The elliptic. So we have elliptic. So we say that the equation is elliptic if the discriminant is less than 0. If the discriminant is less than 0. So our discriminant that we are looking at is what? 16 minus 16 xy then we have less than 0 to make the PDE an elliptic. So from here to we can decide to send our 16xy to the right hand to get positive 16xy. So this will cancel this. We are left with 1 is less than what? Xy, of which we can write it as xy is greater than what? 1. So we are saying that with the elliptic, the equation is elliptic if xy is greater than 1. So with this equation, it is parabolic at xy is equal to 1, it is hyperbolic at xy is less than 1, and it is elliptic at xy is greater than 1. So with this particular equation, it is parabolic, elliptic, and then what? Hyperbolic at the same time. But we are not done. We are not done because the question says determine the region of all points. We want to determine the region for all points at which this equation is what? Parabolic, hyperbolic, and then elliptic. So we are going to draw our x and y plane, our Cartesian plane. Let me write this one here. The elliptic, let me write it somewhere. So we are going to determine all points. We are talking about all points. So let's start with the first one, which is what? Parabolic. We are going to start with the first one, which is parabolic. And its equation is given as so xy is equal to 1. Xy is equal to 1. So this means that when we pick any point on the x-axis, we multiply it by any point on the y-axis, we should get 1. That is what we are going to look at. We are going to pick any 2 points on the x and then y-axis to multiply to see if we are going to get 1. If it satisfies this equation, then we can say that that equation is parabolic on that particular point. I guess we are following. We are going to prove it or use points to determine it. So let's pick a point here. Let's say for 2 numbers that when we multiply, we can get 1. If you multiply, let's say, when you multiply 1 by 1, we are also getting 1. So let's start with 1 by 1. So let's take it that we pick 1 on the x-axis, we pick 1 on the y-axis. So the point will be here. So it means that 1 times 1 is giving us 1. So it satisfies this parabolic equation. So the point here makes the PDE parabolic. You can also see that when we pick the point 0.5 times 2, we are getting 1. 0.5 on the y-axis and then 2 on the x-axis. So we are going to have this point, the point to be here. It is giving us 1. So it satisfies the parabolic equation. Then we can also say that when you have 0, now you can also plot 2 here on the y-axis and the 0.5 on the x-axis. So we have another point here. We can also say that when you multiply 0.25 times 4, we are getting 1 because we have 1 over 4 times 1 times 4. That is giving us 1. So this also satisfies this parabolic equation. So we are going to have 0.25 on the x-axis. So 0.25 will be here and then 4 will be here. So the point will be here. We can also decide to pick 0.25 on the y-axis and then 4 on the x-axis. So you can see that any point here, when we join this point together, we are getting something of this real form. And any point on this particular line, any point on this particular line, will make the PD parabolic. Remember that these are not the only point that when we multiply, we are going to get 1. There are countless numbers that when we multiply, we are going to get 1. Picking 1 from the x-axis and then picking 1 on the y-axis. We are picking the easiest one because we are sketching. So it means that any point on this particular line will make the PD what? A parabolic. So when we join this point, you can see that we are getting a line. We are getting a line. So this is what the equation xy is equal to 1. Now with the same thing, you can see that when we pick a negative number here, we pick a negative 1 multiplied by negative 1, we are getting is equal to 1. So all these points on this line will be the same point on this particular side, because negative, negative, we are going to get positive. So we have this point here, any point here as well. So this is 1, and then we have 0.5 and 2. So we have 2 here, and then 0.5 here. You can also have 0.5 here, and then 2, and then 4, and then 0.25. So you can also see that any point here, all the points on this particular line will satisfy the parabolic equation. So we have any point here, because we want to determine all the points in the region, which makes the PDE parabolic. So we have xy is equal to 1. So we are done with the parabolic. Let's move on to the hyperbolic. So with the hyperbolic too, we are saying that if you pick any number from the x and then multiply by the y-axis, any coordinate on the y-axis, it should be less than 1, right? So let's check and see. So we have xy is less than 1. So let's pick any number from here, any number from this region, and then see. Let's pick 1 multiplying negative 1. So we have 1 multiplying negative 1. Is it less than 1? 1 times negative 1 gives us negative 1. Is it less than 1? Yes, it's less than 1. So it means that it satisfies this inequality. So we have any point here. Let's take this one 4, and then let's say minus 6. So we have 4 times minus 6. Is it less than 1? This gives us minus 24. Is less than 1. Does it satisfy the inequality? It's satisfied. So you can see that any point that we pick here, any point that we pick in this region, will make the PDE what? Hyperbolic. So we have here to be x, y is less than 1. So when you pick any point here as well, let's say this is 1, so you have to pick below 1. When we pick 0.5 times 0.5, is it going to be less than 1? So this is going to give us what? 0.25, and that is what? Less than 1. So any point that we pick here as well is also going to make the PDE hyperbolic. Very, very easy. Let's take this area as well. So when we pick any point here, let's pick a point here. Let's say negative 1 and then 1. So we have negative 1 times 1. Is it less than 1? This is going to give us negative 1 is less than 1. And it satisfies this hyperbolic inequality. So you can say that any point we pick in this area as well is going to make what the PDE hyperbolic. And then let's move on to the last one, elliptic. So with the elliptic, we are saying that when we pick any point from the x-axis, we multiply it by the y-axis, it's going to be greater than 1. So we are going to check it to see if this region is going to satisfy this inequality. So let's pick any point here. Let's say 4 and then 10. So we have the point here. Let's say the point here is 4 and 10. So we have 4 times what? 10. Is it greater than 1? So we have 40 is greater than 1. It is true. It satisfies this inequality. So any point that we pick here is going to make the PDE what? Elliptic. So any point here is going to make the PDE elliptic. The same thing applies to this side. If you pick any point here, let's say what point? 4, and then so this is minus 4, right? And this is minus 4. Minus 4 times what? Minus, let's say 5. Is it greater than 1? This is going to give us what? 20. is 20 greater than 1? It is greater than 1. It satisfies the elliptic inequality. So we can say that any point that we pick in this region as well, any point that we pick in this region as well, is going to make the PDE what? Elliptic. So let's write the name. So here is elliptic. Elliptic with xy greater than 1. Elliptic with xy greater than 1. And then this region is what? Hyperbolic. So we have hyperbolic. Hyperbolic with xy less than 1. And then on this line is what? Parabolic. So this line is what? Parabolic. So let me write it here. So as the question implies, we should determine the region of all points which make the PDE hyperbolic, parabolic, and then elliptic. So we have determined all the points. Any point here will make the PDE elliptic. Any point here will make the PDE hyperbolic. Any point on this line and this line will make the PDE parabolic. Very, very easy and then simple. I'm going to leave the first one for you to try your hands on it. See you tomorrow. Bye bye.